This video covers section 5.5. Section 5.5 is called the Substitution Rule. And this section completes our journey through calculus in Math 2510. This will be the end of Calc 1. This is the last section we have to learn, and Math 2520 in the fall we'll pick up with section 5.6. So today we're going to talk about the substitution rule. Now, in chapter 5, section 5.1 and 5.2, we learned what is the definite integral. We looked at integration. We saw its development from looking at a rectangle and taking one rectangle and saying, what happens if I estimate the area under this curve with one rectangle? We noticed that wasn't enough. And then we noticed that the more rectangles we constructed, the more accurately we were able to represent the area under a curve. And then through section 5.2 and then into section 5.3, we tied that idea of area under a curve to the concept, the calculus concept of a definite integral. And we learned that a definite integral is the limit as n goes to infinity of the sum of those rectangles. That was our definition of the definite integral. And then in section 5.4, we brought together integration and differentiation in the fundamental theorem of calculus. So that's our journey up to this point. So we have learned where the integral comes from, at least a geometric interpretation of where the integral comes from. And then we have talked about what is the definite integral, what are the properties of the definite integral, and we have talked about the mechanics of finding the definite integral using the definition, along with using the fundamental theorem of calculus part 2, what we call the evaluation theorem. And again, we have connected the indefinite integral, the antiderivative is what we learned that was. We've connected the indefinite integral and the derivative together and learned that they are inverse functions of one another. So now that we have our background in integration completed, it's time for us to start talking about how do we integrate. We know how to integrate if we use the evaluation theorem. However, the evaluation theorem only works if the integrand is something that we know the antiderivative of. Example, right? We can all integrate secant x tangent x dx because we know the antiderivative of secant tangent. We know the derivative of secant is secant tangent, and therefore we know the antiderivative of secant tangent is secant of x plus c. So we can integrate only right now, only if we are able to find the antiderivative of the integrand. However, what happens, right? What happens if that's not the case? What happens if they ask us to find the integral of something like 2x times the square root of 1 plus x squared dx? Okay. I've mentioned to you during class that taking an integral is an art. Finding the integral of something is an elegant mathematical exercise, in my opinion. Differentiation is not elegant. The derivative rules work, we write down the function, we follow the derivative rules, we get the answer. Integration requires a bit more finesse. When we look at a problem such as this, where we know the antiderivative, sure, we can find the integral without much effort. However, if we look at a problem such as this, where we don't know the antiderivative of 2x times the square root of 1 plus x squared. That's not an antiderivative that we know. We haven't memorized that. We haven't had past experience with that. So how are we going to integrate that? Well, that's what section 5.5 covers. How does one go about integrating something such as this? And the approach turns out to be relatively non-complicated. It's pretty straightforward. What I'm going to do is I'm going to say suppose, right? Just suppose. And we'll talk about why all of these things are true. But let's just say, suppose we let u. I'm going to introduce a new variable. That's where the name substitution comes from. We're going to substitute a new variable. We're going to let u equal 1 plus x squared. And we'll talk later in the video about why I chose this and what was my impetus for making that decision. Something interesting happens if I take the derivative of both sides of this with respect to x. The derivative of this side is going to be du dx. The derivative of this side is going to be 0 plus 2x. Now, if I multiply, if I treat this like a differential, like we did earlier in our book, back in our section on differentials, if I treat this like a differential, I can rewrite this as du equals 2x dx. And I have an expression for du. Now, if we go back to our original problem, and I'm going to rewrite this problem. Okay, I'm going to change the order. These are all multiplied together. So by the commutative property, I can change the order. I'm going to go ahead and put the square root first. And I'm just going to put a bracket around that so we're not confused. I'm going to put the 2x and the dx at the end. Okay. Now, if we take a look at what we've got written here, right? If we look at this in the context of what we've written over here, this piece right here, that piece, we've called that u, right? And we called u 1 plus x squared, so we have a square root here. So this is the square root of u. Now, who is this? Well, we have called that du. Now, what does that do? Well, that affords me the opportunity to rewrite my integral if I substitute, right, the substitution rule. If I substitute these variables in place, what do I have? I have the square root of u, right? I'm going to rewrite that as the square root of u. I'm going to call this du. Now, that integral is u to the 1/2 du. And that's an integral we know the antiderivative of. We know how to integrate u to the 1/2 du. We have the power rule. And we know the answer to this, right? The answer to this, based on our power rule, is going to be we add 1 and we divide. So when I add 1, I get u to the 3/2. U to the 3/2. When I divide by 3/2, that's the same as multiplying by 2/3, isn't it? It's the same as multiplying by 2/3. So the integral of u to the 1/2 du is 2/3 u to the 3/2 plus c. Now this is what the substitution rule does. The substitution rule takes a problem that we do not know the antiderivative of. By us making an intelligent choice for u, determining du, it affords us the opportunity to do this substitution, and we can end up with an integral that we know how to integrate using antiderivatives, and we get our answer for the integral in terms of u. Now, that's not our final answer. Our final answer is going to be this problem's in terms of x. So our final answer is going to have to be expressed in terms of x. So what do? Well, yeah, you're right. We go back and we resubstitute in u. We know what u is. It tells us right here. We've got it written right here in our paper. So this is going to be 2/3. U is 1 plus x squared to the 3/2 plus c. And this is the answer to the integral problem that we were originally given. This is the integral of 2x times the square root of 1 plus x squared dx. Now, how do we know if we're correct? Well, remember, this is the antiderivative of this integrand. So if I take the derivative of this, I should ultimately end up with 2x times the square root of 1 plus x squared. We can always check our integral by taking the derivative of our solution and seeing if we get the integrand back. So let's do that. let's check, right? This is a check. We'll do a check here. It's not hard to check. We're going to check. We're going to take the derivative of 2/3 times 1 plus x squared to the 3/2 plus c. Right? We're going to take the derivative of that. And what happens? Well, we leave the constant out in front, so that's 2/3. We have something to a power. We're going to need the chain rule here. So we bring down the 3/2. Of course, those multiply together to give us 1. Our new power is 1 plus x squared. We subtract 1. Remember, we're taking the derivative here. We subtract 1, that's 1/2. We have to complete the chain rule, so we've got to take the derivative of what's inside. That's going to be 2x. Of course, c is a constant, so the derivative of a constant is equal to 0. And if we simplify this, right, 3 cancels 3, 2 cancels 2, we have 2x. I'll go ahead and write that first. 1 plus x squared to the 1/2 absolutely is the square root of 1 plus x squared, and that's our integrand in our original problem. So this is what U-substitution will do for us. Now, if you're thinking to yourself that there's something special about this integrand, you're correct. There is. The integrand is written so that the 2x was present, and therefore, when I took the derivative of 1 plus x squared, I generated a 2x dx for my du. The components necessary to build du were present in my integrand. And that's how U-substitution works. This isn't the end-all for integration. This is just our first integration technique other than the antiderivative. From here, not in our class, but from here in Calc 2, you're going to learn many more integration techniques. But this is just the first one we learn, right? The first one. It doesn't answer every integral. It won't solve every integral. It only solves integrals that are structurally constructed so that when I write down u, my du appears. Okay? So it's just for those types of integrals. So, what does an integral that fits, right? What does an integral that fits the format for U-substitution look like? Well, that's what we're going to write into our notes next. So, what did we do, right? What did we do? Well, we'll write this down and then we'll talk about it. It's going to be a lot of symbols, okay? So but let's just go ahead and write it down and see what it says, all right? So we're going to write down the substitution rule. And we're going to write the formal rule down. It says if u is equal to gx. All right? So if u equals gx is a differentiable function, now, if we don't remember the definition of differentiability, a function is differentiable where its derivative exists, okay? Whose range is an interval I and f is continuous on I. Then. All right? So what does this say? We have some function that we're going to choose to substitute in. The u function, this one right here, is the function that we're going to choose to substitute. Now, in our previous example, our u, remember, was 1 plus x squared. And our very next step was to take the derivative of that. So we say if u is a differentiable function, it has to be differentiable because our second step after we discover u is going to be to take the derivative of u. So it has to be differentiable. And f is going to be continuous. Now we'll have to see who f is going to be here in a second. Now this is what the substitution formula says. It says if I have the integral of f of g of x times g prime of x dx, that is going to equal the integral of f of u du. All right? So that's a lot of symbols. All right? There's a lot of functions and integrals there. Let's write that down, and then now let's talk about it and see if we can make it make sense. Okay? Now we've already covered why g has to be differentiable. G has to be differentiable because our mechanical second step, is going to be to find the derivative of 1 plus x squared. And so we're going to have to take the derivative of that. So g has to be differentiable. F is going to have to be continuous because we're going to integrate f. And our definition of continuity says as long as this function is continuous, sorry, not our definition of continuity, our definition of integrable says as long as f is continuous, we can find its derivative. Now, what's going on over here? Well, let's start with the obvious. This is a composition, right, of two functions. And that's what the substitution rule looks for. The substitution rule says if you have a composition of two functions, I can help you out. I can help you out. I can help you find the antiderivative of a composition of two functions. If you have a composition of two functions as one of your factors, and you have the derivative of the inside term, the inside function, as one of your factors, then the substitution rule works. And if we write down what we did just a second ago, right? If we write down what we did, the example we worked on was the square root of 1 plus x squared. That is the composition of two functions. Our inside function is 1 plus x squared. Our outside function is the square root of x. So in terms of our pre-calculus approach to the problem we just looked at, we do have two functions here. We have an outside function that's the square root, and we have an inside function that's 1 plus x squared. So our inside function is 1 plus x squared. Our outside function was the square root of x. Our problem was given to us as the square root of 1 plus 2x times 2x dx. That's the way the problem that we used as our introductory example was presented. Well, if we look at g, the derivative of g is indeed 2x. So this fits the format of what we were working on, or what we have written up here under the substitution rule. This fits the format of what the substitution rule will allow us to integrate. And what does the substitution rule say? It says your answer is ultimately going to be f, right? The same function you have here. F, your integral is going to be f, the square root, not of g of x, not of x, f of u du. And if you look back in your notes, this is exactly what we turned that problem into. So if you would take the time to perhaps pause the video, look at this in your notes, look at what we did here, identify for yourself why f is the square root of x, identify for yourself why g of x is 1 plus x squared, because it's the inside function, Identify yourself that yes, indeed, the derivative of this is 2x, and 2x is a factor of my integrand. You would be able to see and come to grips with what the substitution rule says. The substitution rule says I integrate things such as this. This is what I integrate. Okay. Now again, we can't integrate every function out there with the substitution rule. We can integrate some functions, and in the homework all the functions are going to be written so that we can integrate them. But there are many, 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 way more that we can't integrate than we can by the substitution rule. Unlike differentiation, integration is elegant. We're going to learn several rules, and we are going to have to recognize, oh, this problem right here, this looks like a substitution problem. All right? Now, the beauty of Calc 1 is we stop here. So this is the only rule we know. Therefore, on an exam, any kind of an assessment, if we're given an integral and we look at the integrand and we think to ourselves, I don't know the antiderivative of that, well then the only opportunity we have to solve that integral is to use the substitution rule. That will all change in Calc 2. In Calc 2 we'll learn more integration techniques, and then we'll have to identify the problems. You will definitely have to know this rule and know, oh, this problem looks like that, so I'm going to use the substitution rule, or this problem fails to fit this format, so I'm going to have to use something else that I'm going to learn about in Calc 2. But for now, this is what we do, right? Because this is what we have. Now, I'm going to perform or complete many, many examples of this to prepare you to do the homework. This is all that we cover in terms of the substitution rule in this lesson, but we need many examples before we're going to become comfortable with this. Okay, so I'm going to do 3 examples right now, and then I'm going to add in one cute little integration technique that we haven't talked about yet, and then that's going to close out all the information we need to complete our Calculus 1 course. So let's do some examples, all right? So we have completed an example, all right? We've completed an example where the problem fit, right? The problem fit the substitution rule perfectly. Perfectly. It fit the substitution rule perfectly. So let's look at another example. Okay, let's say that we're going to integrate dx divided by 3 minus 5x, and we're going to square that. All right? Now we have, when we look at this, we could rewrite this. We could rewrite this. There's no need to rewrite it like this, but you could if it makes it easier for you to see what's happening. We could rewrite it like this. And now remember, if we're going to apply the substitution rule, our first instinct is to look for the composite function. Do we have a composite function? And we do. We have 3 minus 5x inside of a square. So if we wanted this, right, if we wanted this to be f of g back in pre-calc, we would say that my outside function, right, we would say, if we were in a pre-calc class and we were talking about this from the perspective of a composite function analysis, we would say, well, what do we have here? Our outside function, right? Our outside function would be the square, and our inside function would be 3 minus 5x. So we would have f would be x squared, right? The square. The g function here would be my inside function, 3 minus 5x. So when we're doing U-subs, that's what we call this, U-subs, because we always pick U as our variable. When we're doing U-subs, we want to identify the inside function and we want to identify the outside function. So those days in pre-calc when they asked us to decompose functions, this is what they were hoping we would be able to accomplish with that skill when we got into a calculus class. We are going to typically, I'm going to write typically, we let u equal the inside function. Okay, it's not always, that's not a firm rule, it's a semi-firm rule. So if I'm going to do this problem, I'm going to come over here on my paper, off to the side, out of the way, and I'm going to say, okay, I'm going to let u be 3 minus 5x. Right? Now our next step, remember our next step is to take the derivative of both sides. The derivative of 3 minus 5x, of course, is negative 5. We're going to treat these as differentials, so we're going to put the dx over here. And now we're going to come back to our problem, and we're going to try to rewrite this, right, as f of u. That's what the substitution rule said. We want to rewrite this as f of u. So we're going to write equals the integral. I'll change colors to show we're working with the new. Now our f is 1 over x squared, right? That's I guess we should have written that up here, huh? So I called it x squared, but it was really 1 over x squared, wasn't it? So our f is 1 over x squared. So that's going to be 1. And remember, we want f of u. We've called 3 minus 5x. We've called 3 minus 5x u. So this is going to be 1 over u squared. Now, what do we have left, right? We have used up 1 over 3 minus 5x squared, right? Now we have a dx. Now, for us to get a du into this problem, right, to get a du, we want to write du here, and we're going to. We're going to write a du here, but we're going to look back at our problem over here, and we're going to notice that we have an issue. 1 du is negative 5 times dx. There's no negative 5 over here. In the previous example we did, we needed a 2x. There was a 2x sitting in our integrand. We don't have a negative 5. Now, luckily for us, that's not a deal breaker because negative 5 is a constant. We have the dx. What we're missing is the negative 5. So what we're going to do is we're going to put a negative 5 in our problem. It's a constant. We can do that. Now, when I say we're going to put a negative 5 in here, I'm going to just take this numerator and I'm going to put a factor of negative 5 in the numerator because now I have negative 5 times dx. Now, we've all taken algebra forever, right? We started in our Algebra 1 class knowing that I can't do that. I'm not allowed to do that. I can't just introduce a negative 5. But I can if I also divide by negative 5. Okay, so this is what we do in a U-sub. If we need a constant, and it's not there, we don't have to panic about that. We just bring the constant into the integrand, and then we divide by the constant outside the integral. Now, negative 5 over negative 5 is 1. We haven't changed anything. So this piece right here, that's why I get to write du. Now, when we look at this, we think to ourselves, well, it's not this, is it? This is really going to become, we don't want to forget that negative 1/5. So our integral turns into negative 1/5 the integral of 1 over u squared du when we do our substitution, because we needed to multiply by negative 5. And the only way we can multiply by negative 5 is if we also divide by negative 5, and so I've done that. Now, this, right, we all know what this is. This is negative 1/5 the integral u to the minus 2 du, right? We're going to write it like that so we can find our antiderivative using our power rule. Now, we know what that is. That's negative 1/5. We add 1. Be really careful when you have negative exponents, because when you add 1, a lot of times we want to make that a 3, but it's not, is it? We add 1. That's going to be u to the negative 1. We divide by our new exponent. We tack on our c. Now, that, right, if we simplify it, that turns into negative times negative is a positive. U to the negative 1 goes on the bottom. So I have 1 over 5u plus c when I get all done. Now, done there is relative, right? Because we're not done. We're not done because this answer is in terms of u and our original problem is in terms of x. So we are going to go back now and resubstitute in who we know to be u. And that's going to get us 1 over 5 times. And who is u? U is 3 minus 5x. Plus c. So if, when we do our U-substitution, we are short a constant, that's nothing to panic about. We just introduce the constant in the numerator, introduce the constant in the denominator outside the integral, and then we can proceed with our U-substitution. Now, is this really correct? I don't know. Let's see. We know how to find out if that's correct. We can check it, right? We can do a check by taking the derivative. If we take the derivative, will we get the same answer? Right? Will we get the same answer? Well, let's see what we get. So what are we going to do? We're going to take the derivative of 1/5. I'm going to go ahead, I don't want to do the quotient rule, so I'm going to write this as 3 minus 5x to the negative 1 power, right? So I don't have to do the quotient rule. Now, how do we take, oh, I'm sorry, I left out the plus c. We know the derivative of c is going to turn out to be 0, but we want to be complete. So what do we get? We get 1/5, right? 1/5. The derivative of this, we're going to bring down the negative 1, right? The new power, we're going to take away 1 because we're differentiating, right? We're going to take away 1. That's going to be negative 2. And we're going to take the derivative of what we see inside, chain rule. The derivative of what we see inside is negative 5. And then, of course, the derivative of the constant equals 0. Now, what do we get here? Well, we have a negative times a negative. That's positive. We have 5 times 1/5. Okay, that's 1. And so we're left with 3 minus 5x to the negative 2, which, of course, is 1 over 3 minus 5x squared, and that's our original integrand. So we got the problem correct. So this example covers what happens, right? What happens if I'm missing a constant? And it's nothing to panic about. You just introduce the constant and divide by the constant out in front, and then proceed with your U-substitution. Okay. Once again, we chose u to be the inside function. And that's typically, remember typically, that's typically what we're going to do. Not always, however, right? Not always are we going to do that. So I'm going to do an example right now that's still a u-sub. It just looks a little different. Okay? It's a classic problem. It's another type of integral that U-substitution will solve for us. So what happens, right, in this example, what happens is somebody asks us for the integral of tangent of x dx. Now, it's kind of strange that we have not, at this point in time, come up with an antiderivative for tangent, have we? We haven't found one of those yet. We're going to get the antiderivative of tangent right here, because now that we know U-substitution, we can go ahead and solve an integral such as this. Now, when we look at this, we do not see a classic U-sub problem sitting in front of us. It's not there. There's not a function inside of another function. That's not a composition of two functions. So this doesn't fit our classic approach for U-substitution. However, this is what I meant earlier when I said integration is elegant. Integration is an art form. Integration is our opportunity to go, oh, wait a minute, I remember doing a problem that was very similar to this, and this is the technique I used, and I'm going to use that technique again, and wow, look at that, it worked. So here's an idea that we need to store and not forget. Tangent can be written as sine x divided by cosine x. Right? We all know that. Tangent is sine divided by cosine. Now, if we take a look at this, again, it's not a composition. It's not a composition. I can rewrite this as 1 over cosine x times sine x times dx. Now, that step right there is not necessary, but it's a step that in the beginning of our journey through U-substitution, I think adds enlightenment. Again, there is not any function that's a composition of another function here. But this is still a problem we can solve with U-substitutions. Because if we take a look at this, right, and we let u equal cosine of x, right, we let u be cosine, then when we take the derivative of both sides, the derivative of cosine is negative sine x. Well, I happen to have a sine x right here. du, when we treat these as differentials, turns into minus sine x dx. And if I take a look at my problem, this, if I introduce a minus here, right, this turns into du, doesn't it? Now, if I introduce a minus inside, I've got to balance that by introducing a minus outside. And if I do that, I get 1 over u, cosine is u, du. This is an integral that we can integrate. We know this. We know what this is. This is minus 1 over u is the natural log of the absolute value of u plus c. So here's another type of integral where we don't have a composition, but we noticed, hey, wait a minute, cosine. Your derivative is over here as a factor. So U-substitution is going to allow me to solve integrals of this type. So we're not done, of course, right? We're not done, because that's solved in terms of u. So the answer here is minus the natural log, the absolute value of cosine x plus c. And you and I, for the first time, right, for the first time, know now what is the antiderivative of tangent. The antiderivative of tangent is minus the natural log of the absolute value of cosine. That's why we haven't written it down anyplace else. We couldn't find it until we learned how to do U-substitutions. Now, this is one way that we can express the antiderivative. Another way, of course, is we have log properties that say we can bring this up here, and if we bring this up here, then that ends up being cosine to the negative 1. Cosine to the negative 1, of course, is 1 over cosine. 1 over cosine turns out to be secant. So there are two ways that we can express the integral of tangent. It's either the natural log of secant in absolute value, plus c, or it's the natural log, minus the natural log of the absolute value of cosine, plus c. It's just a log property that gets us from one to the other. All right? Now, I said I would do 3 examples. That's 2. I'm going to do one more example here. So, what happens if we're given, instead of an indefinite integral, what happens if we're given a definite integral, right? A definite integral to work with. So let's look at a problem, And we'll pick something that, this is actually number 48 from our textbook. We'll pick something that looks relatively intimidating so that when you're doing your homework, perhaps if you run across a problem such as this, instead of thinking, you'll think, wait a minute, I've got this, okay? So here we sit, we have this problem. Now the only difference between this problem and the 3 examples I've done so far, because I've already done 3, is this is a definite interval. So we're going to have to talk about how to handle that, okay? And there's 2 options, and I don't care which option you choose. They both work. One is not quicker than the other, so it doesn't matter to me which one you prefer. So what are we going to do? We're going to look at this, and we're going to think to ourselves, wow, I do not know the antiderivative of sine times cosine. That's not on the table in chapter 4 or the table in section 5.3. So what am I going to do? I'm going to hope that this fits the U-substitution idea, because that's the only other integral technique I know going into, into the end of Calc 1. And so I do have right here a function of another function, right? We have an inside function. And we said, when we have a composition, typically our go-to move is to let U equal the inside function. Now, at this point, let me address what happens if you take a guess at who U is and it doesn't work. Well, then you guess something else, right? There are only a finite number of things over here you can let U be, so you just keep guessing. I'll let U be this. Oh, that did not work. I'll let U be this. Sooner or later, you're going to stumble across the appropriate choice of U. Now, I'm going to go with my rule that says I should try the inside function first. Now, that means then that du is going to be sine x dx. Notice I skipped the middle step, because the middle step is always du dx equals sine x, and then we move the dx over. So typically, we don't write out all 3 steps. We just do that in our heads. All right? Now, that's completely wrong. I was spending so much time thinking about how I was going to point out to you that I was skipping the middle step, that we all know the derivative of sine is not sine. The derivative of sine is cosine. Now, when we look back at the problem, we have a cosine, right? They gave us a cosine right here. So this piece and this piece multiplied together make du. So when we rewrite this, right, right now, these 2 pieces, right, these 2 pieces come together and they give us a du, don't they? Now, what is this? Well, this is sine. We haven't done anything with that. And we have called sine x u. So this is sine u. Sine of u. Now, here's where things get important when it comes to definite integrals and U-substitutions. All right? So you're going to want to pay particular attention here. Take good notes. My variable is now u. Right? My variable is now u. This question asks me about a lower bound of x equals 0 and an upper bound of x equals pi over 2. Right? We don't draw it, but somewhere over here, there's on the x-axis, we're starting at 0, we're ending at pi over 2. This is the x-axis. Right? That's the x-axis. That's not the u-axis. Now, why do I bring this up? I bring this up because we can't put 0 here and pi over 2 here, because our variable is now u. And those are x's. So if you write them down, then what you have written is incorrect, and your teacher is going to mark it incorrect. You have to be aware of what you're working with here. You have changed variables. So you have gone to the world of u. You are no longer on the x-axis. You're on the u-axis. And on the u-axis, we don't move from 0 to pi over 2. So what do? I just leave the integral like this. I don't put bounds. I leave no bounds. I integrate sine. We all know what the integral of sine is. It's negative cosine u Now, because I have a definite integral, I'm not going to write a plus c, right? Definite integrals, their antiderivatives have a constant of integration. Definite integrals do not. Definite integrals are numbers. We don't get a plus c. We don't get a function there. So I have minus cosine of u. Now, that's not my answer, right? Because that's still in terms of u. So now what do? I come back and I insert u. U is sine x. Now this is very important. X is back. Right? We're back in the world of x. We're back on this interval. So we're going to evaluate this between 0 and pi over 2. So there are no bounds. Don't write bounds here. If you write bounds here, well, let me rephrase. If you write 0 and pi over 2 into this problem, I'm going to be forced to mark that wrong. You're going to get the wrong answer. Even if you write it down and don't use it until you put x back, merely by writing it down, you're telling me that u goes from 0 to pi over 2, and it does not. X does. So don't write that down. Now, what is this going to give us? Well, we know what this is going to give us. This is going to give us negative cosine of the sine, right, of pi over 2 minus, right, fundamental theorem of calculus, minus negative cosine of the sine of 0. And we can figure that out. We can all draw the graph if we don't know what sine of pi over 2 is. It's not a big deal. We can all draw the graph. This is pi over 2. Sine of pi over 2 is 1. So this is negative cosine of 1. Now, I don't know what that is, right? I don't know what cosine of 1 is. If I draw the graph of cosine goes like this. This is pi over 2. Pi over 2 is bigger than 1. 1 is some number over here. That's not any special angle. I don't know what that is. So I'm going to leave it as negative cosine of 1 minus sine of 0 is 0. Right? Sine of 0 is 0. See, it's right there. So this is negative cosine of 0. Cosine of 0 is 1, so that's negative 1. But then we have another negative, so that becomes plus 1. So our answer is 1 minus cosine of 1. So when we do U-subs with definite integrals, we have to be very careful that we do not put the x variables into the u integral. Right? That's just wrong. We don't do that. So we're going to save our variables, save our bounds until we get back into the given variable that they give us in the problem. All right? So those are our 3 examples. We're now prepared to go out and do the homework in section 5.5. Oh, I'm sorry. I forgot about the one last thing that is in section 5.5. So let me clear this off and talk to you about the very last idea that I'm going to teach you in Calc 1. And this goes all the way back to pretty much the beginning of our pre-calc journey when we meant symmetry. So the very last thing we're going to talk about, the very last thing we're going to talk about is what happens, right? What happens, and so we'll draw a graph here. What happens if we have a function, like say a parabola that's symmetric, right? It goes from negative a to a. So it has symmetry. And this is y equals f of x. Now this doesn't have anything to do with U-substitutions, right? It doesn't have anything to do with that. It's just this is where our author decided to put this into our book. He says, what happens if I ask you to integrate from negative a to a of f of x dx when f is even, right? Being even means that we have y-axis symmetry, right? Well, what does this equal? Well, if we look at this area right here is exactly the same as this area over here. They're exactly the same. Due to the symmetry, they have the same value. So what our author says is, hey, maybe if you wanted to, you don't have to do this, it just makes things easier. Instead of integrating from negative a to a, you could integrate from 0 to a. You could find me this piece right here. And if you're going to do that, that's going to be fine. It's not the real answer. The real answer, of course, is to find that piece and then to multiply by 2. Now, why do we do that? Because we get a bounded integration of 0. And it makes our life better. Right? When we do our evaluation theorem, instead of plugging in the antiderivative at a minus the antiderivative at negative a, we get to plug in the antiderivative at a minus the antiderivative at 0. Much nicer arithmetic typically occurs when we notice this. So remember, this is true when f is continuous on negative a to a and f is even, right? We have y-axis symmetry. Now what about when we have a function that's odd, right? Let's think about our graph of sine. Sine looks like this, right? And let's call this negative a, and let's call this a. Well, what do we know about this area right here? We know this, if I call it a, we know this area because it's below the x-axis. This is going to be minus a, right? And so if f is odd, and they ask us to find the integral between negative a and a of f of x dx, we get this positive piece plus this minus, this negative piece, so we get a net answer of 0. Now, that's really nice. Saves us an awful lot of work. So remember, that happens when f is continuous on negative a to a and f is odd. Right? So those are two little things that we don't want to forget. They could save us a lot of time as we move through calc. Because keeping those in mind is going to make, every now and then in Calc 2, that's going to pay off. It's going to save us a lot of time. Even in Calc 3, it's going to pay off. All right, that's it. We're done. So, thank you. That completes section 5.5.